Hello everyone. Hope you are enjoying good health and happy life. I am Muhammad Asif. And for A level chemistry, our next chapter is chapter number 24, transition elements. What are the transition elements? These elements are defined as those D block elements which have one or more stable ion with partially filled d orbital. This is the most important thing to note. Those ions which contain one or two different types of ions of elements in which partially filled d orbital is present. This is important point. Those are called as transition elements. These elements in the periodic table are present between second and third A groups. And there are three series. There are three series of transition elements. Three series of transition elements. For example, after calcium, first series start. After calcium of second group, first series start, which starts from scandium, and after scandium there is titanium, vanadium, chromium, manganese, Mn, iron, cobalt, nickel, copper, iron, cobalt, nickel, copper, and then finally zinc. This is the first D series. Second D series starts from yttrium, then zirconium, niobium, after niobium, technetium, molybdenum, then technetium, and then ruthenium, and after ruthenium there is rhodium or X, and then PD, palladium. After copper there is a silver, and then after zinc is cadmium. This is the second D series. Now there is third D series. We will just discuss only first transition series, transition elements. Now, as the proton number of calcium is 20, so the proton number of scandium is 21, scandium is 21, titanium 22, vanadium 23, 24, 25, 26, 27, 28, 29, and then 30. If we compare all these elements, these first group of these transition series, scandium, yttrium, and lanthanum, and the last group of D series, zinc, cadmium, and mercury. These are the elements. These are the elements which are called as non-typical transition metals. While these elements, all these are called as typical transition elements. Why? Why these are called as non-typical and these are called as typical transition elements? The reason is in scandium, yttrium, lanthanum, and in zinc, cadmium, mercury, there is no partially filled d orbital present in any cation are called as non-typical transition elements. While all other elements, their one or more ions contain partially filled d orbital. That's why these are called as typical transition elements. Now, we are going to discuss now electronic configuration of these elements. Now, one by one, if we discuss the electronic configuration of scandium, if we start from here, the proton number is Z is 21. Electronic configuration will become 1s2, 2s2, 2p6, 3s2 and 3p6, and then 4s. How much electrons will be there? 10 and then 8, 18 and 3 electrons left. Now 4s2 electrons, how many electrons left? Then 3d1, only one electron will come in 3d orbital. 1s2, 2s2, 2p6, 3s2 and then 3p6, 4s2 and 3d1. This is the electronic configuration of transition element scandium. As we know that whenever the electron will be removed by this metal atom to form a cation, definitely 2 electrons from 4s will be removed first. As a result, due to the removal of 2 electrons, positive 2 charge will come on the scandium. And if along with these 2 electrons, 1 electron from D is also removed, then the cation will form with positive 3 ions. But the most stable electronic configuration of scandium exists by positive 3, and with positive 2 oxidation state, scandium exists less stable. Now, if we discuss the electronic configuration of titanium, proton number will become 22. When it will become 22, what will happen? The d orbital will contain 2 electrons. In the previous one, when 4s electrons and 3d electrons will be eliminated to form scandium with positive 3 cationic charge, automatically there will be no partially filled d orbital left over. That's why scandium is considered to be a non-typical transition element. But in case of titanium, look at this, with proton number 22, 4s2 and 3d2 electron will come. What will happen? Now, there will be 2 oxidation state produced, positive 2 if 4s electron will be removed, and positive 4 if the 2 electrons from d orbital will also be removed. But in this case, along with positive 2 and positive 4, there is another oxidation state, positive 3, that can also be developed, due to which this titanium becomes a typical transition element. Next is, for example, vanadium. The proton number of vanadium is 23. What will happen? Now, d orbital will contain 3 electrons. Now, whenever cation will be formed, when 2 electrons from 4s will be removed, positive 2 charge will come. Then 1 electron along with these 2, positive 3 charge will come. And if 2 electrons from 2s and 2 electrons from d, positive 4 charge will come. And automatically, then if 2 electrons of 4s and 3 electrons of 3d will be removed, then positive 5 oxidation state can also be produced. All these oxidation state can be developed, but the maximum stable are those in which the cation contain unpaired electron and partially filled d orbital. That's why these are called as a typical transition elements. Now, if we look at chromium, here the different scenario will be produced with 24 proton number. Definitely there will be 4 electron in d orbitals. Now, here another situation is created. If we one box, and d electron with 5 boxes. Each box represents one separate orbital. The 4s electron can be represented here. And if 4 electrons come according to Moore's rule, all these electrons will remain separate in the different orbitals rather to become paired in the same orbitals. Now, as only one electron is short from the stability of this d orbital, that's why to make this d orbital maximum stable, one electron will shift from 4s to this 3d orbital. And both of these will become exact opposite that will enhance their stability. That's why the with these 6 unpaired electrons, the chromium can easily attain positive 6 oxidation state in so many its compounds. For example, K2Cr2O7, where the chromium has a positive 6 oxidation state. This is the matter of chromium. Now, what will happen with case of manganese? There is total number of electrons 5. Now, what will happen? 2 electrons and 4s will remain, and the 5 electrons will present in separate d orbitals. Now, whenever these 2 electrons is removed along with these 5 electrons present in the d orbitals, definitely the manganese can adopt maximum of positive 7 oxidation state. Positive 7 oxidation states. That's why the highest oxidation state, highest number of oxidation states can be attained by the manganese, which starts from positive 2 to positive 7, but the maximum stable oxidation state compounds are known, and less stable oxidation state compounds are not very common. That's why they are not considered too much. Now, the same situation also comes after iron, after cobalt, after nickel. In copper, this situation just like of chromium appear once again. For example, if we perform the oxidation state of copper with 29 proton number, what will happen? Now, the d orbital will contain how many electrons? 9. Now, how these electrons will be adjusted? 4s will contain 2 electrons, and these 9 electrons, 5 electrons are distributed, and then in the second round, all these unpaired electrons will become paired, and only one unpaired electron will exist. Now, to gain the maximum stability, this d orbital then can gain electron from 4s to complete its d orbital. Now, d orbital is complete, only one electron left behind in 4s. That's why this is a copper in which +1 oxidation state due to the removal of this one electron can take place. But whenever one electron from 4s and one electron which is shifted into d orbital, copper will definitely attain Cu positive 2 oxidation state. But when copper will attain positive 2 oxidation state, there will be 9 electron d orbital, it will become partially filled, automatically copper positive 2 ion will show different colored compounds. But if the compound of copper 1 chloride is observed, no colored compound it can form, this will indicate that in case of Cu positive 1 and d orbital is complete, that's why in that situation it also becomes a non-typical metal. But in case of Cu positive 2, it becomes a typical metal. These are the different oxidation states of the ions which are produced by all these typical transition metals and how the electronic configuration they attain. Next is important their physical state. Now all the transition metals are normally number one have high melting point and boiling points. High melting point. Second, these have high densities. High densities. Third, these have high densities. These are hard normally, except mercury, Hg, which is in a liquid state. These are good conductor of heat and electricity. Heat and electricity. And these are the good conductor of heat and electricity. These are very hard, due to which these are normally used as a construction material for our daily life. These metals are very useful, and especially the magnetic substances like iron that play very much important role in our life, in industry and in so many others. These are the physical properties. We have already learned that these transition metals with the partially filled d orbital will definitely formulate or produce colored compounds, and the non-typical transition metals will never give colored compound. That is due to the d-d transition of electrons. Now, if we discuss their atomic radii, generally we have observed that from left to right, as we move in the period from left to right, generally the size of an atom decreases. But if we look at the transition first series, there is no big change in their atomic radii. Why? Because the d orbital is involved in the completion phase. That's why so many electrons can be adopted quite easily in the d orbital. That's why the increase of the nuclear charge, number of protons in the nucleus, the force of attraction of the nucleus on the electrons become more stronger and stronger. That's why the atomic radii never change too much from left to right in the d series. In the similar manner, their cationic radii will also remain same, and due to this factor, due to same size, due to this approximate same force of attraction of the nucleus on the electrons, and their first ionization energies will also be a little bit quite similar. Now, if we compare the properties of calcium with the first d series, the size of calcium atom and ion will be much larger as compared to all these typical transition metals. Density of calcium will be lower as compared to these typical transition metals. The melting point of calcium will be lower than these typical transition metals. Similarly, the conductance, the calcium is more good conductor in comparison with these transition metals, because in case of calcium, due to the larger size, the force of attraction of the nucleus on the outermost shell electron is less. That's why those electrons can easily be moved from one point to another, and that's why calcium becomes good conductor as compared to all these, with one exception of copper. The conductance of copper is more as compared to calcium. The reason is the arrangement of the copper atom in its metallic crystal that provide a very easy or safe straight ways for the movement of electron. That's why. Now, these are the some physical properties and comparison with the calcium, how the typical behavior of calcium with these transition metal appears. I hope you have understood all these concepts which I have explained. Thank you.